All right, Dave.
Hello, everybody. We'll get started in just 1 minute. Welcome, everybody. We'll be getting started in just a minute or so. Letting a few more people in. Shane, I'm looking at you for a thumbs up when we're ready to go. I think we got a thumbs up. Well, welcome to our next installation of a webinar. Fortunately, you can't do this in person, but fortunately, we can still hold these and have all you guys here. We're really excited to have Janice Cohn here to talk about some of the work that we're doing within one of our working groups, all focused around extreme weather and wildfire events. For those of you, if it's okay with everybody, just to make sure it's public that we're recording this event. What we're going to talk about today, Shane, if we can kind of go to the next slide, is we're going to go over just the larger project context, what it actually is, and what Pyregence actually is, and then we're going to do a deep dive into the microscale weather work that Janice is leading. We're hoping to leave about half an hour at the end for Q&A. We're hoping that it's going to be a rich conversation. We have both Shane and Justine are monitoring the chat, so feel free to put stuff in there, and we'll have a little wrap up at the end. Can we go to the next slide, Shane? For those of you who aren't familiar with Pyregence, it's a consortium that's really focused on trying to understand what's needed to build the next generation of wildfire models. It's a public-private partnership with academics all included. Here's a list. Here's a logo board of some of the different organizations that are connected, and there's more. If you go to the next slide. Here's a list of some of the names of the folks that are part of this program. We're inclusive. If this is something that you're interested in or want to learn more about or want to figure out how to collaborate with us, we're very open to that. Please reach out. Reach out to us. Shane is the program coordinator for this effort, and he could air traffic control you to the right place. Next slide, please. You look at the program itself, we're broken out into 4 main working groups. The first 2 working groups are really focused on trying to fill some gaps between base research and applied research. And then the second 2 programs are trying to figure out how to take some of that applied research and put it into some practical tools that could be used for the benefit of ratepayers. This is a CEC funded project, a CEC funded program, and we're very privileged to have them. So working group 1, if you look at working group 1, that's where our extreme weather extreme weather and weather station optimization group actually sits. It's a group led by Janice. I'm going to put a pause on that. She'll dig into what we're doing over there, but there's several other folks that are involved in that group. Our second working group is fire behavior and fuels mapping, is led by Scott Stevens. The purpose of that program is really to understand what our fuel profiles consist of, how they're configured, and how fire behavior actually operates inside of them. The idea here is to upgrade a lot of our existing understandings and relationships between surface fuels, canopy fuels, and fire behavior itself. So there's a lot of work going on that. Next working group is led by Chris Lautenberger, the near-term forecast and modeling systems. We call it Pyregence. The idea here is how do you take those learnings from the first 2 working groups and give us a near-term forecast of 5-day forecast in an operational setting, both for active fires and overall statewide risk. And then our last working group, which is led by Leroy Westerling, is really honed in and focused on our long-term risk projections. Think of 100 years out. And the idea is that if we can get a short-term understanding of fire effects on the grid and long-term understanding, then we can start making strategic decisions and tactical decisions in a way that's consistent to protect our infrastructure, environmental assets, so on and so forth. So Can we go to the next slide? Some of the principles that kind of guide all of our research. It's a science-based program. Science. It's not an advocacy group. It's we're trying to lead everything using a data-driven approach, open data approach, open data science. That's something that's really important to all of us. So everything that we produce, all the information products that you actually see will be made available. It's really guided by user needs and operational experience. So it's a needs-driven approach as well. The idea, we really fall in line with the idea that collaborative science is needed to solve some of these large-scale issues. So we really take a collaborative approach across both sectors and disciplines and research programs. So we really try to reach out to other research programs that might benefit from what we're actually doing. We do the same thing in reverse as well. And then we also have a technical advisory committee, and that purpose of it is just to make sure the stuff that we're pushing down, we don't get into too many rabbit holes, and the stuff that's being produced or the science that's being pursued is actually useful and consistent with existing operations and institutional practices. With that, I'd like to pitch it right over to Janice. This is her working team, and Janice, can you take it away from here?
Thanks, Dave.
So Janice, I'll stop sharing, and then you can go ahead and jump on and share your screen.
How's that?
Need you to expand your slides. There you go. Perfect. Thank you.
Thanks for the introduction, Dave. Today, and first, thanks everyone for joining us. I know these Zoom meetings can be tiresome, so I'm really grateful for you sharing your time to join us with this aspect of the Pyregence project. I'll be talking about some of the work I'm doing with colleagues for the extreme weather component of the project, but also integrating some related work from other projects I'm working on for NASA NIST. And that brings in contributions from Wilfred Schroeder, my longtime colleague in NESDIS, Andy Prine and Abby J at NCAR, Lee Tarnay, who's at the Forest Service, Nancy French at Michigan Tech, Kathy Butler at NIST, and Doug Stowe from San Diego State. So this component of the project, some of the impetus and priorities mentioned by the CPUC directing this area of work. We have extreme wind events, and these are a critical factor in many of our recent California wildfires, but the historical data and the methods we have for reconstructing the winds have been insufficient in given us conflicting information. We know there's climate change impacts on California risk. What's often mentioned are changes in the temperature and moisture deficits. I'm moving your faces out of my screen there. Through the moisture deficits, long-term dryness events like droughts and subsequent impacts on the trees and their mortality. But along with that, perhaps less mentioned are changes to the atmospheric circulation. And the projections of the future give us conflicting information about whether these events would decrease, increase, or persist in their frequency and other characteristics. And then there are some combined effects, the changing seasonality of the wildfires and the evolving vegetation under these persistent seasons of intense burning. There has been tremendous action among the utilities to better instrument the wildlands, to give us better information about the weather events, the winds within some of these canyons, to give better information about where extreme winds might occur. There have been impacts on drought and tree mortality, as working group 2 is investigating how these might impact fire behavior through the buildup of some heavy ground fuels and the intense mortality across the Sierras. There's been what a great degree of work in investigating how wildland fires can penetrate into the built areas, causing destruction, and our ability to model these is somewhat limited. We focus on embers, both produced by the houses and also what the methods through which they're ignited, but there's other aspects that I'll touch upon here today. We talk about extreme fires by the numbers. Of course, only a few ever exceed 100 hectares. If you look at the figure on the right, a power law distribution describes the number of fires in a given size category. So while there are many, many small fires, there are very few that ever get to be exceptional in size. But this largest 1% account for 80 to 96 of the area burned. So they're disproportionate in their impact. Also, as we looked over the historical satellite record, mapping burned area over the past few decades, the days with very large daily fire growth are still very infrequent, only a few per year. And we find that these extreme events, these days of extreme fire growth, occur from I hate this term, but a perfect storm of factors at different scales. One is an underlying susceptibility due to broad, slow changing factors, like a very dry season in the Southwest, on top of which is a period, 1 to 5 days, of locationally specific weather. Certain weather patterns are problematic in certain areas. And on top of that, it requires a fortuitous ignition at the right time and place to take advantage of it. So we're looking at these extreme events from a combination of these factors coming together at once. So we're looking at historic fires and what conditions led to these extreme events. One is through extreme weather typing, where we're identifying regional weather patterns, characteristic weather patterns that associated with these past days of large growth. And in other work we don't have time to discuss today, Andy Prine can tell you more about the historical trends of these patterns and how they might, what climate projections are suggesting might happen to them in the future. But along with that, we're looking at fine scale deconstruction of some of these key events to try to understand the local airflows and how the fuels and terrain condition came together to produce these days of unusual activity. And we're doing that with convective scale weather simulations that are tied to fire behavior models to investigate what factors caused these events to unfold as they did. And along with that, we're looking for conditions where we know some of these extreme wind maxima come. David came up with the accurate term hotspots. There are certain hotspots in the landscape that are predisposed to generating some really extremely unusual wind maxima that are sometimes connected to problems with the electric grid. So to characterize these historical fires, we developed a methodology called extreme weather typing. And we're looking for regional weather patterns that are associated with days of large daily fire growth. And in this, we break California into 8 rather distinct regions that have similar fire environment and behavioral types. And by bringing together atmospheric reanalyses, these are all the data we collect about the atmosphere stitched together in a physically consistent manner with a numerical model and data assimilation to give us gridded information about weather at consistent periods throughout the past. And we're comparing that with the data set. We have a few decades now of satellite active fire detection data that tells us about burned area. And Andy adapted a cluster analysis he developed for identifying weather patterns associated with extreme precipitation events, and he's adapted it to this problem to try to identify these weather types associated with very large growth. And this paper is in review now at the Journal Geophysical Research. So on the right are these different regions, and here are some of the characteristic wind events that we know. There are some others, the no-no winds and so forth, but we've broken these apart because of the different fires in these different regions. So we use these daily burned area products to accumulate all the daily burned area in each of these regions. He selected the top certain number of days, you can say certain number 4 that are at least a week apart, and he tried to identify the atmospheric variables that characterize these conditions objectively. And so he tested these 33 variables from the reanalyses, and these are some of the dynamic forcing variables. These are the winds and pressure, thermodynamic forcing, the temperature and moisture at various heights in the atmosphere, and some indices that tell us how susceptible the atmosphere is to vertical lifting, and that would be to develop the deep pyrocumulus, and to test their ability to predict these daily extreme burned areas. He tested all possible combinations of up to 3 of the variables to identify which ones had spatial gradients that had the most predictive skill for burned area. An example with a pattern that you might see from these daily burned areas is in the lower right for the Los Angeles area. There really are only a few per year with some standout events. So what we've found from this, it is true that the most extreme fire growth days were associated with these archetypal weather patterns. Some of them are familiar. They're mapped on the right. These are some are familiar, the downslope wind events, the Santa Ana's and Diablo wind events, but others are less so. And I haven't seen mention of them in the scientific literature. There's a clear seasonal cycle with summer and autumn maxima. And we find that these extreme fire days dominate the burned area statistics. Only the top 1% of days account for between a third to more than 2/3 of the burned area statistics. So the unusualness of these extreme growth days carries over to these to the burned area statistics. So what that means is the rapid increase in decay in these daily burned areas indicates that these extreme fire days are really closely related to short-term weather more so than slowly changing factors, these background factors. And this is in agreement with previous research that came about it from different methods. So if we look on the right, the figure, I know this is really complicated and this is laid out in the paper, but there are some distinct types here. Along the coast, in the Bay Area, the Central Coast, LA and San Diego, these areas have 2 basic types, an offshore wind event that we're very familiar with, but another pattern associated with large daily fire growth is a weak onshore flow, and these feed some of the large plume-driven events. In the Sierras, some of the more common types are, well, in some of the internal regions are a thermal low. These also direct wind gently, weak wind conditions up the west side of the mountain slopes, feeding plume-driven fires. Other regions are dominated by pressure, wind systems dominated by troughs and ridges. These are weather terms that describe patterns in the surface pressure, and these influence the low-level winds across the complex topography. So these allow us to characterize fires by types and flag days with the potential for exceptional fire growth. If we look at Los Angeles, as I mentioned, there are two major types. And what we see for each of these types, Andy was able to find the pattern, these regional patterns associated with the extreme weather type, how long they characteristically last. For example, the Santa Ana winds are 6-day event here, and another type is the 4-day weak onshore flow. He tells us about, his analysis tells us about the seasonality, the monthly occurrence frequency, what months of the year these are most common. Of course, the Santa Ana winds, there have been some odd ones in May, but also these are most common in September and October into later in the fall, whereas the onshore wind events are most characteristic of the large fires in June and July. And he also identifies the patterns that if you were looking at daily weather patterns, you could identify by looking at these patterns that one of these events is imminent in the weather forecast. And these map across a very different type of fires. The Santa Ana wind events is characteristic of these offshore wind events, whereas the second type is more characteristic of plume-driven events that start at the base of a topographic feature, generate their own winds, and draw themselves up the slope. So we have these for the different regions. I'll not go through them in detail. They're in detail in the paper. I think you could contact either Andy or I for that as it appears. I guess sometimes these identify a large regional dynamic event like these offshore flows. Some are these weak onshore flows, but others, the pattern is that the fires must have evolved from small scale local factors, because there's no strong indicator in the regional pattern what would be driving those fires. So they're generating their own circulations from very small local factors that we can't identify from this analysis. In the northern region, this is the one that still kind of mystifies me a bit. Most of the large fire events are driven by pressure systems that are either a trough. This is what we mean by a trough. It's kind of a dip in the picture. In the one on the left, a ridge. This is a high pressure ridge because it goes up and down, and some of these other patterns that bring air preferentially through the topographic features and create local problematic winds. The MODOC, this is the northeastern part of California. These events are often driven by dry, high-base thunderstorms that set off gusty fires that can spread over very great distances over the shrubby MODOC National Forest area. Curiously, if we look at the Sierra West, we often think of these downslope wind events. This analysis it picks up two types, this trough behavior on the left and this high thermal low pressure that allows the upslope fires to flourish, but it doesn't pick up the downslope events as part of the largest events. You might see changes in these types if we accumulated more data over time. If you look at the top 20 events, then some of those downslope wind events become more significant. So we should think about how we might update this methodology with data as it becomes available, because some of these weather types might emerge as more prominent in the future. If we look at what happened during 2020, one type was the Diablo wind events in September, but the August fires, it didn't flag, it didn't pop as one of the types we'd already identified. So what was this? This pattern had occurred in 1985 when we look back through the historical record, but it didn't cause large fire growth then. So it wasn't flagged. Dave Sapsis mentioned having remembered this event, although I think he's far too young to remember what was happening in 85. So he must have meant his father or grandfather remembered this event. This event was associated with onshore convection forming out on over the ocean and moving onshore and being associated with dry lightning. So in August of last year, it created very large fires, but in these past episodes of it, approximately 15 and maybe 30 years ago, it did not. And that was because it had the ability to create downdrafts and strong surface winds that created large fire growth. So this methodology picks up many things, but it should be used, updated in the future as some of these events emerge. Also, some of these factors are combination of events that this methodology doesn't yet pick up. For example, lightning doesn't pop from this spatial gradient approach. So there's still some work to be done to make it more complete. So that was a long-winded explanation of what weather types can produce large fire growth. As we transition to these finer scale factors, again, I'm reminded to mention this multi-scale analysis. For one of these large events to occur, we need an underlying susceptibility. For example, last year we had widespread vapor pressure deficit, dryness over the entire Southwest. On top of that, we had favorable weather patterns. And on top of that are local factors. These can be the topography, shape, and features, atmospheric stability, and some of these airflow dynamics that can unfold into events like the Woolsey fire, a wind-driven fire, but also in these other types, these can combine with inclined canyons, heavy mortality, fuel loads, and a gentle nudge and ignition at the right place to set off some of these big plume-driven events. So part of this approach has been to catalog the susceptibility to these types of events across California and to place it in some kind of knowledge framework so it can be used for practical use. So some of the mechanisms for extreme growth. Rapid fire growth occurs at either end of a spectrum. We usually classify fires as wind-driven or plume-driven, depending on which appears to be driving fire growth. And in fact, both of them have very strong winds, but in plume-dominated fires, the ambient winds are usually weak, and the strong winds are generated by the fire's heat release, what we call fire-induced winds. At the other end of the spectrum are the wind-driven fires, where the ambient winds are strong and the events are associated with exceptional wind events like we've seen in the past. And both of these types of events can appear mysterious because they're the weakest link of the current tools in one way or another. The plume-driven fire-induced winds aren't captured by our current operational tools. And at the other end of the spectrum, these complex airflows in mountainous terrain are very difficult to model. And some of the simplest tools that can be done in a rapid manner aren't sufficient for capturing these complex mountain airflows. Just a brief background on this airflow and complex terrain. As we try to understand what's going on in California, one of the things we appeal to are some idealized flows, and this has been described quite well in books and scientific literature, one of which is Mountain Meteorology by Whiteman. He describes some of these possible flow regimes that can happen when air moves over terrain of various shapes and sizes. And some of the important parameters are the atmospheric static stability. This has to do with the lapse rate, the rate at which the temperature decreases with height. On a hot sunny day, the boundary layer is well mixed and air can be lifted up and moved down and there's no restoring force. On other days when the ground is cooled overnight and you create stable airflows, you would notice these with capped inversions like you might see in over cities. That means the air is resisting vertical motion. So when you have air that's resisting vertical motion and you lift it over terrain, it feels a force that tries to bring it back down to the level at which it's at the same temperature of the air around it. So this restoring force creates a lot of the motions we see in the atmosphere and associated cloud patterns. But it can do many things depending on the static stability, the wind speed, particularly near the mountain top, and the aspect ratio or the slope of terrain. If you have neutral flow, air tends to go smoothly over a bump as shown in the lower left here. And you might get circulation patterns around the back of it. So these are little eddies and the airflow might go over the top of it. If the air is going much faster, you'd see a different effect, whereas the airflow separates from the mountain and there's a circulation underneath where the air is very almost still. It's a stagnation region. If the air is stable, and this is important for some of the California airflows, you might see a variety of features. As the air goes over a mountain, you might, as we see in Colorado, see vertically propagating gravity waves. So these lines are lines of constant potential temperature. That's a term we use in meteorology. If the potential temperature is the same throughout the atmosphere, then the air is neutrally satisfied. There's no stability. You can move it up and down at will. But in conditions like this, the potential temperature increases with height. The air is stable. When you lift it up, it tries to return down to where it was before. So it creates a number of wave effects. These can propagate up into the atmosphere, or on the lower right, you see under certain conditions, you can have trapped waves in the lee of the mountains. Anyway, this is horrible mathematical stuff. It's a niche area in meteorology and it's very mathematical, but it's important for what we're doing now. This is very complicated stuff, but it has tremendous impact how these work. So those are some of the idealized cases. When this first came, these issues with the wind events in the electric grid first came up, we tried to turn for information to analogs in other locations. One of what we had at the time were a lot of studies in atmospheric gravity waves, so waves created by airflow over the Colorado Front Range. And many people had studied these. We tried to draw from these to understand what was going on in California in the Diablo and Santa Ana events. And this is horrible mathematical stuff, just horrible. As the airflow is lifted over the mountains, we talk about vertically propagating waves, whether they become so steep that these wave crests we create tip over the top and break like waves on water waves on a beach. Do waves reflect from certain profiles in the atmosphere? And then the question was, do these really apply to California events. And well, thank goodness they don't. California's these wind events are very different. So this is a new regime. We don't really have information to draw from. What we have in some of these wind events is high-speed winds coming off the Great Basin. They back, that means rotate counterclockwise with height. So while the surface winds are coming from the northeast, the winds rotate with height so that they're coming from the west in the mid-atmosphere. Accompanying that is almost always this very stable layer of air near the surface. So there's this river of air that doesn't like being lifted up over terrain, being pushed from the Great Basin over ranges, down river canyons, through cracks in the mountain range to try to get to lower pressure offshore. This isn't a good example, but you can also see these, you can often see these stable layers in the Las Vegas sounding. And then you combine this with these complex topographic features, and you get a really odd regime, which hasn't been described in the science literature. So this is kind of a new area, but the one good thing, well, the interesting thing is it doesn't support waves. So a lot of what we know from other places doesn't apply. If you look at a schematic of one of these wind events, you have high pressure over the Great Basin, and it works its way over the Sierras down the Central Valley and fans out over the coastal range. And in the Southern California, you often have preferential strong winds down several of these river canyons. There's a great deal of variability across California, and surprisingly, there'd been little examination of the details of these airflows in either of these types of events. So the California events are unique, and we don't have a lot to draw from, and there are science gaps for us to that we need to fill before we can achieve our objective for this project. So if we look at one of these events, the Napa firestorm of 2017. Okay, so I have some animations, and Zoom isn't playing nice with them. I've tried different things, but I'm going to try to do the best I can with them to manually move you through these so you can see how these events evolve. So this was the Napa firestorm of 2017. It was a strong Diablo wind event. And here, this is my simulation at about 3 kilometers of the region in that area. So I'm deliberately not showing you the arrows in detail. I want you to see the effect of them. The more rapidly moving air is shown in the hotter colors like yellow and red. The less rapidly moving air is shown in the cooler colors of blue and purple. So throughout the, this is a day and a half of event. This is the winds in that area. So there's a great deal of variability even across this area. Some areas, some of these peaks are putting off pulses of air up 30 to over possibly 40 meters per second. Other areas like up north in the Redwood Valley area are showing steady streaks. So even in one event, there's a lot of variability across a very small region in terms of how this event affects the local winds. And it's going to do that. The model I'm using is a numerical weather prediction model tied to fire behavior. It's optimized for looking at fine scale simulations in very complex terrain. If you were to compare this to some of the other fire modeling systems, these tools, you might think of some of the other project systems, Elmfire, Gridfire, Farsight, some other tools you might be more familiar with. These have the same sort of inputs that are directed directly into the fire behavior model, but the difference here is the numerical weather prediction model is tied to fire behavior. So the weather and the fire behavior are feeding back and forth at every time step. The weather as it varies, the wind as it varies in time and space directs how the fire spreads and how fast, and the heat released from the fire, that is the change to the temperature and the water vapor, are fed back into the weather, altering the winds in its near environment. And that allows us to better model how the event unfolds. It helps us to understand transient behavior in fire, how a fire evolves and splits, how fires merge, how it changes direction, how gust fronts from the pyrocumulus above evaporate and change the direction of the fire. It helps us model where fire worlds are going to form. So there's much more complexity in it, but it produces many more things we're interested as we're trying to investigate why fires behave the way they do. I think we'll skip this. The fire behavior module is very much like you're used to in some of these operational tools, but what's different here is that the way they interact at each time step, so that even while we are using things that are very similar, like semi-empirical rate of spread relationships, where the rate of spread, the Rothermel formula, is a function of fuel properties, but also modified by factors related to the wind and slope. Even though we're using that as in the kinematic formulas and some of these operational tools, it's done very differently here, in that the wind directs the fire to spread faster, which releases heat, which makes the fire spread faster, which releases more heat. And again, this feedback allows the fire to amplify and develop winds that are 10 times perhaps as strong as the ambient winds. And this captures some of the mass fire effects, what people would call blow-ups or firestorms, through the ability to develop these, what we'd call internal dynamics. How we do this for an event, we model weather over the Western US, and we focus down through grid refinement to look at a particular fire area. We bring in information on terrain elevation and fuel maps, how these fuel models and fuel properties, we can use custom information, how they vary across the landscape. So we're modeling large scale weather, and we're focusing down to 100 meters or so, maybe 300 meters in the area of a fire. And this is an order of magnitude more refined than the national weather forecasts are done at. So this is the roadmap for the rest of this presentation. We look at these wind-driven events, and we're trying to classify problematic areas. And as I said, there's not much to draw from in the scientific literature, so I'm kind of poking around in the dark and finding things that are important and trying to put it in some sort of knowledge framework so that we can develop an understanding that can be used in more practical applications. So some of the things that have turned up problematic winds, weather patterns, are the terrain aspect ratio. We can distinguish that the Sierras are steeper than some of the other more gentler rounded ranges, the transverse ranges and the west coastal ranges. That's a significant difference. There's a distinction whether the airflow goes over the range or through by various means. If the flow goes over the top of continuous ranges, we have certain types of flows that occur in the lee. There are different effects and problems that arise where the flow goes over the range, but there are notches or saddles in the range. For example, broad dips that when the pressure is pushing from behind, the airflow rushes through this lower notch. There are also these river valleys, east-west river valleys, notches in the Sierras, and these create certain flow effects that are problematic in some of the fires I'll show in a moment. There are other different types of issues with flow that goes between. For example, more so down in LA, in the LA region, where the airflow doesn't go over a mountain range, but through some of these broad river valleys and passes. So that's one set of problems. Another is where there are intersecting airflows. There's some local anomalies, and the transients in these events is an important component in creating these excessive winds that impact the grid. And I'll touch upon the contribution of built structures, although most of that work is happening in the other work group. So this is a roadmap of some of these events I'm going to discuss. One example was the Woolsey fire, and starting with probably the simplest airflow that occurs, although I guess it's not very simple in a big picture sense. The Woolsey fire in the LA area, we're approaching it with a simulation that models airflow in the Western US and focuses down to 185 meters in the area where the fire ignited in the Santa Susana Field Laboratory. So this occurred during a Santa Ana. It was, when we do this simulation and look at the airflow in this area, the Santa Susana Laboratory is in the lower left portion of this region. We see there's a narrow river of strong winds. There's a region of strong winds that are the width of this mountain pass. And you can see the gusts. So the stronger winds are colored again in the hot colors, and there are pulses being generated by the upwind mountains. And these are occurring, if we look at a time series of the max of the winds at the ignition area, there's every 2 minutes this repeats. The winds vary over a 4 meter per second pulse. And these are largely coming from the this transience is coming from the upwind mountain range. As they go over the flows, the ignition site, and over this mountain range, it's about as simple as it gets. This is a Bernoulli-like airflow acceleration as the pressure drops going over the topographic feature, the airflow speeds up. So this is pretty simple. There's some transients in this, and if we look at a cross section of that all-important potential temperature, we see there's stable air near the surface in the cooler colors, and it's being lifted up into weaker air, and you see some of these wave-like crests. There's some disturbance in this lifting, so it creates some more pulses in the air at the surface, but there's no dramatic flow effects. This is pretty simple. If we look at evaluation, we should always look at evaluation of our simulations. This is a simulation of that period. On the right, the extent of the fire created with compared to the VIIRS map at a similar time. So it was splitting into two parts and coming downhill to the freeways. A similar event, the Witch Creek fire from 2007, exceptional by many standards throughout the historical record. I'm sorry, this is going to be herky-jerky, but I think I can keep it smoother for you if I move the slider myself. So this is looking at a period at the ignition of the fire. Again, the hotter colors are indicating stronger winds. These are at the first surface of the model. So near the surface, but not immediately at the height of the measurement of the surface stations. So these pulses are coming off the mountain ranges. You can see the ignition of the fire. It's pretty simple, as in the previous example. If we look at a cross section of the winds, it's simple Bernoulli-like flow. The ignition was pretty much at the top of a ridge coming out of this canyon. So simple, but very strong pressure force driving it. The fire spreads. I've lost my pulse. There it is. Each one of these frames is 1 minute apart. The fire spreads downwind. I'll ignite these other fires as they were detected. First, the Witch Creek fire, followed by the McCoy. Losing control. So the fire spreading downwind. A map of the incident is shown in the lower right. So this is kind of a simple airflow, but the winds were strong just by the basis of the pressure gradient. So we have ignition of the McCoy. Similarly, and this unfolds and flows downstream. So this is another problematic scenario for strong winds. I should mention Shane's going to upload these, so you'll be able to download them and see them more clearly from the Pyregence website. A different type of flow occurs in the coastal ranges. Elsewhere in the coastal range, this was the Tubbs fire. This was a part of the 2017 firestorm, and if we focus on this particular area, the VIIRS map of the fire is on the right. This event occurred in the lee of a ridge. If you were a meteorologist, you would expect the strongest winds on top of the ridge. But what happened here was, as the winds passed over the ridge and went over some secondary ridges, that's where some very strong winds were generated. And that's where the ignition occurred. So as the fire spreads downstream, again over a very broad range, a very shallow range, the south flank encounters a topographic feature and draws itself up, accounting for this bulge on the south flank of the fire as it spreads down into Santa Rosa. So what was unusual about this, there's our comparison. We should always compare our simulations with an observation. This is another one of those unusual scenarios that I haven't seen anywhere else in wildfires. So it's a shallow range. You don't see the strong winds over the top, but they occur on this secondary bump where the ignition occurred. So we have this unusual situation of high speed flow of air that's very resistant to being lifted. There are surges from upstream topographic features that are moving through. We would expect to see more effects from the stability, but it's moving so fast, there's no time for them to have the effect they should. So what we see are, I'm really kind of stumbling, I'm sorry. What meteorology would tell us is this behaves like the neutrally stratified flow, that Bernoulli effect, and it mostly looks like that, but there are eddies of exceptionally fast air being shed off these secondary mountain ranges that boost the peak winds up another 10 or 20 meters per second. So we have some interesting effects in the topographic regions. In that same event, the Redwood Valley fire further up the coastal range. This is a different type of effect. It's a very narrow, about 12-kilometer wide river of strong winds that it was produced when this strong pressure gradient pushed air through a dip in the upwind range. So there's a very narrow range of strong winds. And within that river is where two ignitions were triggered. There's one, and there's the second ignition, and they're at the edge of this river. Interestingly, at the time, if we try to figure out, was this detected by the weather stations? Weather stations at the time wouldn't have detected this. They're indicated in this figure in the upper left by these crosses, and most of them, well, there's one that lies just at the edge of it, but most of them wouldn't have detected this region of strong winds, which passes between them. They can often be pretty far apart before the utilities have been supplementing them with further information. So we need another problematic area. We need to look at gaps where there might be downstream gusts, and these attribute some of those streaks that we saw in the regional airflow. The campfire was a different animal. So we're moving to the Sierras, much more steep terrain. This is a simulation of the event from ignition throughout the first day of growth. Again, the strong winds are indicated by the hotter colors on the arrows. The ignition occurs down in the river valley at a location where the winds are simulated to be elevated, and the fire is driven rapidly downslope with these pulses of winds through, first up onto this lava plain, and then downwind, down the lava plain, encountering paradise from the side. Here, you can't, no, I didn't mean to do that, sorry. Your pictures are right over where my time arrow is. So this is about when the fire encountered paradise. We're modeling a continuous line of fire. So even though the satellite images are showing active fire over that, most of that was spotting. So we're representing the fire at landscape scales. This includes all processes, including the long distance spotting. What's important about that event is that you couldn't reproduce that rapid spread of the fire without some really gnarly fluid dynamics. If we take a vertical cross section down the center of that fire and we look at the potential temperature, again, this indicates the stability of the air. Heavy, dense air is at the bottom, and it's being bumped up into less dense air by these topographic features. And what it does is create these wave-like features which crash backwards. And when they come crashing down to the surface, it creates one of those pulses. And in the right is a figure of one of those pulses showing these peaks in the wind speed. The peaks in the wind speed are shown by these darker pulses. So as these winds come down to the surface, bam, 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 they're creating these scallops of wind that drive the fire down slope. If you were to try to model that with the community model WRF, other people have looked at this event. Brewer and Clements looked at the weather, and that weather looks like what you would observe, like winds on the downslope. But when it's coupled to fire models, they're woefully inadequate at reproducing the fire spread because of some properties of that model. It's very diffusive of fine scales. It doesn't maintain these sharp gradients in the temperature in the stratified air. And without that, you can't reproduce these strong winds that drive the fire down slope. So the problem I see in that, in the rush to adopt a model like that as a forecast, is that it doesn't reproduce the fire spread through the town, even in the first day or even by the end of the second. And it would make catastrophic predictions of the event. It would produce predictions that would tell you to stay safely in your home in paradise, that the fire would never reach you. So I think this is problematic in the way some of these advances are going, and the introduction of these systems and some of the predictions they're making about these unusual weather systems. A different type of event, the North Complex. This is modeling winds through a break in the Sierras. This is at the bottom end of the Feather River Canyon. Of course, we're all concerned about the Dixie fires starting not too far above this canyon and above this fire and running up into the Sierras. This was a moderate frontal event. The winds, there are strong winds down these frontal faces, but the strongest are within the drainage. I call this the Drano effect. If you look in the lower left, this image of the fire is contouring the winds at 3 kilometers above ground, and I colored it by the vertical velocity. So over the canyon, you see this sinking. This is really hard to visualize, but in this layer of air, you can see air kind of sinking down into the canyon, like you might see in a drain in a bathtub. This is characteristic of winds in some of these moderate wind events.
Hey, Janice, I just want to do a quick time check.
Yep.
Okay.
We have problems with intersecting airflows, and that's an example would be in the Carr fire, where we created this giant fire whirl over the town of Redding. A simulation of this event shows there are problems that occur when airflow up the Central Valley intersects with airflow coming down over the coastal range. And where they intersect at this boundary creates a shear zone. And when the fire runs across it, you create the Carr fire whirl. So simulation of that event. Okay, so airflow is coming up from the bottom, up the Sacramento Valley, and from the left over the coastal range. And where those intersect is in the west part of Redding. And when the fire runs across it, you create these fire whirls in the area where it was observed. The timing and the travel direction it traveled is really complicated, and you have to get everything right. But you do see these whirls that are created right in that area that burned intensely and spread over Redding. A local anomaly, this was really odd. I just completed this. We have the esteemed fire researcher, Chris Dykes, taking a selfie in front of the Blossoming Creek fire on the September 5th. What was unusual about it, when I look at the VIIRS data, often you see this active fire shown in red. As it spreads over an area, it kind of decreases rapidly, but in this case, it stayed red. So these areas were burning consistently for over a day, and that indicates some heavy fuels. And the heavy mortality and the effect on fire behavior is something the other groups are looking at. When we look at the evolution of this event, ignited in progress, this was a really unusual one. You start to fire in progress, and there's not a strong synoptic figure, but as the fire grows and it spreads north, it creates a strong mesovortex of its own. If you look at I hope you're not going to go. There's a vortex that forms over the north end of the fire. These bring air in a circle near the surface, intensifying the burning, creating a very deep updraft. Can't move my hands fast enough. Here we go. So this mesovortex creates a deep plume throughout the atmosphere, and the heat from the fire stretches the vortex. So like the spinning ice skater, she twirls faster. So this intensifies and builds a very deep vortex. I guess more, if we look at a vertical cross section of the winds above the fire, rising elements, updrafts, are shown in red, and descending air elements are shown in blue. So over that region of the fire, you see the generation of these very strong updrafts that exceed 25 meters per second. And you can see the rotation about the core of this vortex. So I think this was one of the, I haven't had time to look at this in detail, but it seems to indicate a reason, the local factors that create this vortex between the general upslope of the canyon and these local circulations around topographic features that start off the vorticity, but the strength of the vortex intensifies it and creates the spinning and accelerates the spreading of the fire over this period of time. We'll be looking at that more detail. Finally, we have some events that have wind-driven event components that have wind-driven components, wind-driven periods. For example, the Thomas fire, this had a period where winds were blowing over the transverse ranges. Some exceptional winds in this area caused two ignitions that created this wind-driven portion of the fire. But then even though this event went on for a couple weeks, it looked very different a couple days later. What was a wind-driven event, while we have a Santa Ana still blowing, there are portions of the fire that are reaching up into the transverse ranges and having periods where plume-driven growth dominates the fire. And we have some evaluation of those periods from the VIIRS data. So some areas of the fire might be affected by Santa Anas, whereas other areas are being affected by plume-driven growth. So I think finally, we looked at the WUI fire problem. Part of this has to do with embers, and this, I've stolen this figure from the NWCG, and it talks about WUI fires, the problems being in terms of embers being generated, lofted, and igniting when they land. But I think the way I look at it, it's much more complicated. We're modeling embers in outdoor topographically modified airflows. We have fire-induced winds from the consumption of wildland fuels. Houses are being ignited by embers, but they're also producing them. These embers are being lofted in an updraft that's enhanced by these fire-induced winds, but the structures, the communities are also releasing a lot of heat. And the question was, is this heat a significant factor we need to look at when we're modeling community events, WUI fire modeling events? They're also creating factors like fire whirls, which intensify the burning. So one of the tests I did was to say, if we could, where we know we have urban fuels and where we know they were consumed, what effect did that have on some of these events? And if we look at the Tubbs fire, which I showed you, the fire which burned down into Santa Rosa, the original simulation is on the left. When we include WUI fuels, that is fuels that represent the effect of the release of the houses. So they're heavy fuels, but they release heat over a much longer time. Another analogy to this would be the heavy loads that we see in the high mortality areas. This can indeed affect the spread of the event. In this case, it created such a strong plume, it slowed the fire's progression, which made it more like what actually occurred. But it also created fire whirls along the edge of the fire, specifically in the areas of the Fountain Grove neighborhoods. There are fire whirls as the fire entered the Fountain Grove neighborhoods and also as it spread down into Coffey Park, as these were noted in the news. These fire whirls can create much more intense destruction and, of course, are an additional safety hazard. So we have to consider that communities are not only suffering from wildfires, but contribute to the ferocity and the magnitude of their own destruction. I won't I think we'll just save this for another time, but plume-driven fires are another issue. Done some simulations of those effects. What controls it? Not necessarily what you think. Varying the fuel and moisture content over the natural range of possible values didn't really affect the outcome of a fire like the King Fire. It was really limited by the weather window and to the topography. When it got to the top of a river canyon, it ran into rocks. So some of these fires are naturally limited. But as we saw this year, certainly the Dixie Fire was not. While it started out as a plume-driven event, as it reached the top of the terrain, it continued burning, driven by some wind events. And this kind of reflects back to some things Andy had found in the weather typing, raising the question. His results raised the suggestion that back-to-back periods of these XWTs might be increasing, which raises the possibility of more events like the Dixie Fire. And also you see when fires run to the top of these canyons, we had an odd one in Colorado. It's spotted over the Continental Divide. So sometimes they're not as limited as they might appear to be. So this is my last. What I wanted to suggest is what we're doing here with this multi-scale approach is a template for applying in other areas, looking at the regional weather patterns, local wind flows, which might be problematic and lead to extreme fire growth, and the seasonality of these weather patterns overlapping these susceptible periods. This is a real scientific gap. There's not much to draw from. And I look at this as a different way to estimate fire risk. We can look at things like the fire weather index, hot, dry, windy, but this combined multi-scale approach is another way to get at looking at the potential for fire danger in upcoming weather forecasts. So thank you. I've gone on longer than I expected, but thank you very much for hanging with me. I have to acknowledge my sponsors.
That was a lot of information, Janice.
Yeah, too much. Like you told me, keep it high level, right?
No, you did great. You did great. There's a lot of questions that are popping up in the chat as well. I don't know what's the best way of doing this. Maybe.
So, yeah, I mean, I can, Justine and I have been kind of tracking these, and I can call people out, or I can just read what they've submitted. I've got a question here from Randy Striplin, and then Randy, feel free to unmute yourself if I didn't get it right. But his question is, will there be maps of areas of susceptibility to the various extreme weather types? Perhaps separate maps of California for each extreme weather type showing gradient of susceptibility. And then Randy, if you want to unmute yourself to clarify, please feel free to do so.
I think you nailed it. I think it's pretty clear, but perhaps not. See what Janice has to say.
We're going to distribute the results of the extreme weather typing through Pyregence, both through the website and other ways you might suggest. And within each of those regions and those weather types are associated with fires that are characteristic of them. So I see linking those as somewhat important, but certainly the weather types for each region are going to be distributed. Is that what you meant, or did you mean a secondary?
And it sounds like there may be a chance for us to provide feedback if it looks like, you know, we might see some ways that might be more helpful. That
of course.
Yeah. Okay. Good. Thank you.
We welcome that.
Great. And then Heidi Caswell from Pacific Core, you had a question. Heidi, I'm going to let you go ahead and read your question, or just reiterate your question. You're still on? All right. Maybe she's having a hard time getting unmuted, but I'll read it. So it says, does the coffee model or wind flow estimation view the science of wind somewhat similar to wave flow mechanics? She's asking, as a civil engineer, wondering about the tools that are used in solving for such phenomenon. She's remembering the modeling to rationalize how to design breakwaters and such, and wondering if there are parallels that are or can be drawn here. She recalls models and empirical results with proper scaling for various variables in the fluid equations. Sounds like a question that only Janice can answer.
These are really complicated airflows. It would be nice if there were simpler tools, and I know some are being distributed through the Forest Service, that take this awful system of partial differential equations and throw away some of the terms to create tools like Wind Ninja or other flow estimators to make it simple. But the ugly fact is that some of these flows are simply transient, and we throw away time-dependent terms. We can't reproduce the flows, and they're simulated as something different. So I don't know that there's a simple way to use simpler tools to get at these answers. But I think I was hoping what we would be able to do would be to make people aware of what the possibilities are and how they arise. And because even with all the additional stations, there's really not enough information to show you what's going on out there. So by creating a better image in your head, you can seek out information to confirm or disprove your hypothesis about what the airflow is, what it actually is. So anyone can have these tools. I mean, anyone's welcome to run it. I'm not sure, and we're talking about ways to do that. Right now, I don't have a good way to teach everyone what's needed to do it. But we'd like to have more conversations with you, how we can better support these needs through different ways in the future. Dave, do you want to add to that?
Yeah, one of the things that we're intending to do is to try to integrate the coffee model with the elm fire model and the grid fire models to make it easier, to make it more accessible. And also to lock it into some of the other learnings that we have from some of the other working groups, like we talked about fuels beforehand. I also see that there's a question here from John Janice that talks about fuel loads. In work group 2, we're looking at how fuel loads, different structures of fuel loads impact different behavior. But the question that he's asking is, have you examined how fuel loads impact wind patterns?
Yes, and in a variety of different cases. It's somewhat different for the wind events than the plume-driven events. So I was actually dreaming about that question from you last night, John Keeley. I was thinking John Keeley is going to ask me about how does fuels affect these fires. And certainly across the wide range of fires and situations, fuels can be a critical issue in whether a fire spreads or not, particularly in the types you're looking at. In these events that I've drawn from, the most extreme ones, when there's already underlying susceptibility likely and widespread dryness, so the continuity of the fuels aren't really in question. Whether there's continuity, whether it's all sufficiently dry to ignite ignitions. These are more what Rocco Snart in Colorado Fire describes as Bucky's bad day, where all the factors are against you. In these cases, the fuels aren't necessarily limiting a limiting factor. They do have varying importance. Where they are most important and actually where our measurements are off by a factor of 3 to 5 when we compare them with LiDAR data are on the inclined forested slopes. And there they have the most potential to have changes in the outcome of the fire through their ability to create these feedbacks and amplifications where the fire draws itself rapidly up these drainages. But as we saw in some of the other events, I think they can have impact in fires going downslope, less slow in most of the wind-driven events, but sometimes when you get these heavy fuels, whether it's from structures or from the heavy loads, we've seen it in Colorado where you create a plume in a downslope wind event so strong that it's pulling air in from ahead of itself, and heavier fuels or drier fuels might actually slow it down. So there are some complexities to it, but in most of these events, we're already so far out into the extreme that the fuels aren't a make or break issue. But certainly through their distribution of the heat release, they can affect the fires over time, but some more than others.
Thanks, Janice. That was helpful. And excellent talk, by the way.
Thank you so much.
Shane, do you want to go to Scott's question? Maybe you can
Sure.
and have him ask it.
Sure, Scott, are you around still, or should I go ahead and pose it?
Hi there, I'm here. So Janice, thank you for the presentation. I'll just reiterate my question so that everyone can hear it. I know you glossed over the mountain wave effects in the interest of brevity and simplicity. However, you mentioned that the mountain waves don't occur in California. I was just looking to clarify if I understood that correctly, or if you were simply trying to state that it's not the hydraulic jump feature that was studied in the Front Range. And if you could elaborate on that, maybe as well what data you have to support those claims.
Thanks. You do get mountain waves in California, but in these scenarios of the downslope wind events, the Santa Anas and the Diablo winds, that rotation of the winds with height, which isn't a critical level, I think some people are calling it that, and this low-level stable layer, it's not mathematically possible to sustain vertically propagating gravity waves with those conditions. I think this is a whole different animal. That under other conditions, there are many situations where people have studied waves in the Lees and T-Rex and down in the Owens Valley and so forth. But in these Santa Ana Diablo wind events, the setup is so consistently unusual with this river of stable air near the surface that it's not capable of producing vertically propagating waves, which is the predominant mechanism in Colorado. I think I keep mangling this instead of making it clear. Did that help?
Yeah, no, thanks for the clarification.
Okay, is it Joseph Mitchell or Merrill? I guess I had to double check here and see.
Joseph Mitchell.
Mitchell.
Oh,
Joe Mitchell.
Okay,
Hi.
sorry, we have a Merrill that we work with at a CEC. So sorry, Joseph.
Okay.
Go ahead and ask your question.
Yeah, fantastic presentation, Janice. My question was regarding the extreme weather typing. Some ignitions are coupled to weather, such as utility ignitions and lightning, and some are not. Have you looked at correlations between the ignition source and the extreme weather types causing it?
No, I haven't done that. But that's a good idea. Let's talk later.
Yeah, sure.
Okay, thank you, Joseph. Kristen Allison, are you still there? Basically, the question is, Janice, could you provide some info on the mountain effects and how that differs in Southern California, please? So maybe that's a follow-up with Kristen.
Yeah, I did a real-time forecasting experiment for my own, I guess, as a prototype during October 2019. So during some of those wind events, I got to see some of the possible flow effects, and they look somewhat different in Southern California than along the Sierras, both because of the topographic, the aspect ratio, the more gentle slopes of many of the mountains, although you have like the San Bernardino Mountains, which are very sharp. But in Southern California, there are wider mountain passes, so some of the issues become channeling of the flow between the mountains as well as airflow over the top. So some of the peaks are sharp enough to create a shadow safe from the Santa Anas in their lee. In other cases, we're looking at fires that are shaped by passage through some of these well-known passes, Banning Pass, the Santa Clara River Valley. Those are a little better documented in the literature, but what we saw in some of the events during that forecasting period is some of the extreme winds are on some of those islands of topography, mountains that are within those rivers in the Ventura Valley. I'm totally mangling this. I can't think anymore, I guess. But I was hoping there would be more instrumentation on them to understand better what type of flows we're getting, but I don't have a whole lot of information on them. But we can, with the existing models, anticipate the maximum winds down those valleys and when they're going to be able to make it over mountain ranges or over some of these features or not. I think I'm just making this worse, but I'll be happy to follow up with you more a little later, if that's okay.
Yeah, that's
Janice,
great.
I think we accidentally skipped a question up on top. I was scrolling down when we started. There's a question from Michael's iPhone. Michael, on the iPhone, can you unmute? Do you want to ask your question?
Hey, how you guys doing? My background is threat detection at scale, and I've been shocked since I started doing deep research in this field around 2014. Who is responsible for these signals? What I see is that we kind of wait on these fires through 911 and maybe some other aggressive maneuvering, but really not localized and focused on specific areas. We have more than enough information to know where these outliers, if you will, are percolating, yet we're not ahead of the curve. So my question is really simple. I tried to address it from an entrepreneurial perspective, and I can't. There's no way that I can own a fire signal. So my question is, who in the government, in the state government and the federal government, is responsible for these fires beforehand, so we can put together aggressive teams that hunt these things in real time? And my opinion, we're going to have to start looking at very aggressive mitigation efforts. The physics of this problem is just too significant. Now, does that mean that we can design kamikaze drones to put these fires out when they're small? We could. I think we're just gonna have to open up the suitcase a little bit and figure out what the challenges are.
Michael, thank you for the question. I know that's part of the conversation we're having in the larger consortium, but this specific working group is really trying to nail down the difference between the base research and applied research in terms of extreme fire weather events. What makes fire really complicated, it's different than a lot of the other perils. because it's not always an act of God. Sometimes it's anthropogenic in nature. So if you look at the way we have our infrastructure built as a society, it's not geared up for an individual organization to own a signal, right? It's responsibility split between organizations. The science is split between different thematic areas, and the management of it is really regionalized or localized in its effect. So that's one of the reasons why we're having such a large.
If I may, real quick, and I
Yeah.
don't disagree with that. The problem is that once the signal is localized, it's owned immediately. Someone owns it. We figure it out. It goes through 911. We localize it. We say it's owned.
Oh, so I was talking about more of like the predictive warnings.
Yeah, that's my point. I mean, we're getting hammered here, folks, year after year after year, and we're not applying basic threat detection mechanisms and techniques and methods and models that have been proven over hundreds of years. And we're going to continue to get spanked until we do. So my question is, I guess my statement is, somebody's going to have to own the signal, and then we can take this amazing research that's being done and apply it. I mean, we're not applying this stuff in real time is where the challenges are coming in. Anyway, I think this is great work. I just, until somebody owns this signal, no one's going to be responsible for it. So we're not going to get ahead of the curve, and we're going to continue to get hammered.
Yeah, well, you know what, we're at time, and this is a good conversation to continue. So Michael, if you can get your contact information, just make sure you send it to Shane, and I'd like to follow up on this conversation.
Sure. Thank you, Shane. This was really informative. I appreciate it.
Yeah, and then there's also one other last comment with Olivia. It'd be cool to incorporate some of these mapping effects into the wildfirerisk.org site with the Forest Service. So we are collaborating with that group to see how we could take the learnings from all these different efforts and pull them together. The Forest Service is part of this consortium, and they contribute to the overarching effort as well. With that, I'd like to personally thank Janice for leading this conversation. And if folks do have questions, not just Michael on the iPhone, but anybody else, our contact information is right here. You can go to the website too and subscribe to some of the emailing lists that we have and future webinars. With that, thank you very much. Have a great day, guys.